Cool. All right. So this big enough, I think. So this will be this is probably the last week that we will be talking about mechanics, which incidentally is also the last week of before the mid-semester break. So when we come back, we'll talk about different things, but we'll start from where we've left off. So we've started talking about rotating objects. We defined their rotational variables in terms of kinematic variables. Then we looked at the rotational dynamics, applying torques and how torques are able to make objects rotate. So in this lecture, we will talk about angular momentum. So angular momentum is a property of the rotating objects. That's an object that's rotating about a fixed axis. So the angular momentum relates the angular velocity of the object to its moment of inertia. And if we compare that to the linear momentum that we learned before, linear momentum equals mass times velocity. And we've derived equivalent quantities. We said that in linear motion, mass is defined by the inertia of the objects. In rotational motion, mass is equivalent to the moment of inertia I. Linear velocity v is equivalent to angular velocity omega for a rotating object. So we can also draw analogies between rotating objects and objects that are moving in a straight line. So instead of linear momentum P, we're now talking about angular momentum L. All right, so angular momentum is a vector quantity. And if we look at the relationship, this definition for angular momentum, moment of inertia is a scalar quantity. So the direction of angular momentum is influenced by the direction of the angular velocity omega. Of course, in terms of magnitudes, we don't care about the directions. Right, so how do we determine the direction for angular momentum? It's the same as how we determine the direction for angular velocity. So when we, in our very first lecture about rotations, when we talked about angular velocity, we learned that we determine the direction of angular velocity using the right-hand rule, right? So say, for example, I have this wheel, I spin it around in the anti-clockwise direction. So you curl your fingers in the direction of rotation and your thumb points in the direction of the angular velocity and therefore the angular momentum. If I rotate the wheel in this orientation and still rotating it this way, so again, you curl your fingers in the direction of rotation and your thumb points in the direction of angular velocity and also angular momentum, right? So you can see here that the direction of angular velocity and angular momentum sort of depends on the orientation of the object. So so there's something to be aware of there. Okay, moving on. So if we look at Newton's second law of motion, so recall we talked about torques creating the rotation, and we said that if you have net external torque, then the torque will cause angular acceleration. Yeah. So this is the summation. So this symbol here means summation, which is just adding up together all the torques. Net external torque gives you angular acceleration times the moment of inertia here. So if we let's just derive some relationship for the net external torque in relation to angular momentum. So if we recall the definition for angular acceleration, it's the rate of change of angular velocity, right? So how quickly angular velocity changes gives you angular acceleration. And if we substitute that to the definition here for the Newton's second law of motion, then we have net torque is equal to the change in the angular velocity with respect to time. So you still have there the moment of inertia being carried over and angular acceleration being defined by this going into this equation. So you have this derivative of angular velocity with respect to time defining the angular acceleration there. Right, so we learned that this thing, moment of inertia times angular velocity, this is equal to angular momentum, right? So then we can write this expression as the net external torque is equal to the change in angular momentum. So we've just written down, angular momentum in terms instead of angular acceleration there. So we then have an equivalent expression of Newton's second law of motion for rotation, where a net external torque is required to change the angular momentum of the object. Yeah. All right. So yeah, so you can think of Newton's second law of motion in terms of rotation as the object will maintain its angular momentum with some angular velocity unless this system, this object, is acted upon by some external net torque. Right? So say, for example, if I stand in this, if this is a rotating turntable, I have to be careful. All right, if I stand in here and I sort of have some rotation, I need to have some initial rotation here. Right, so I push myself there. That's too fast. All right, whatever I do, even if I try to twist my body, I cannot make myself stop because there's no net external torque acting on me, right? I twist my body, it's still internal. I need someone to please stop the rotating. Okay, and I hope I'm not dizzy. But you see there, I was spinning myself. Need some support. So I was spinning. I have some angular velocity, and therefore I have some angular momentum. No matter how hard I twist my body and try to exert some torque in order to stop myself, I'm not really able to stop myself because I'm part of the system, right? I'm part of the rotating object. I needed Cameron to provide this net external torque, and this external torque, so it has to be an external torque, changed my angular velocity, eventually making my angular velocity 0 and therefore changing my angular momentum. Yeah. Right, so it's net external torque. Again, I emphasize it's external torque that's needed to change the angular velocity and the angular acceleration and therefore the angular momentum of a rotating object. Right? Okay, which means therefore that say if there is no net external torque, in the absence of external torques, the sum of torques is equal to 0, and therefore it follows that the change in angular momentum should also be 0. Right. dl over dt, that's the derivative of angular momentum with respect to time. As I've mentioned many times, if you're looking at just a finite time interval, then the derivative becomes a change. Therefore, the change in angular momentum with respect to some time interval is equal to 0, which means that the final angular momentum should be equal to the initial angular momentum. Yeah? Right, and that sort of is a familiar concept where we learned before that the final momentum, linear momentum, is equal to initial linear momentum. And so it also follows that angular momentum is conserved because the final angular momentum is equal to the initial angular momentum as long as there is no net external torque being exerted on the system. Right, so we can expand further the definition for the conservation of angular momentum. Right, the angular momentum of the rotating object remains the same if there's no net external torque. So final is equal to initial angular momentum. Angular momentum is defined, recall we defined angular momentum to be the moment of inertia times angular velocity. So therefore the final moment of inertia times the final angular velocity should be equal to the initial moment of inertia times the initial angular velocity. Yeah. Right, and momentum is always conserved, just like linear momentum is always conserved. Angular momentum is also always conserved in this case. Right. Okay, any questions so far up to this point? So yeah, what we've done so far is define what angular momentum is. It relates moment of inertia I with angular velocity omega. We've also defined the Newton's second law of motion for rotating objects in terms of angular momentum. Net torque is equal to the change of angular momentum with respect to time. And if there are no net external torques acting, then angular momentum is conserved so that the initial is equal to the final angular momentum. Okay, so let's test some conceptual understanding here. So if, say, for example, you're holding a spinning bicycle wheel while you're standing on a stationary turntable, and if suddenly you flip the wheel over so that it's spinning in the opposite direction, what do you think will happen to the spinning turntable? Will it remain stationary? Will the turntable start to spin in the same direction as the wheel before flipping? Or will it start to spin in the same direction as the wheel after flipping? So have a little think of what will happen while we set up this little demonstration. Right, any answers for what you think will happen? Okay. Maybe we can have a look and see what will happen. And I'll be the one. Hopefully it won't fall off. Okay, so let's recreate the scenario there, stationary. You have a stationary, yeah, I should face it. Stationary turntable, camera will right, so notice how the wheel is turning clockwise. Yeah, so you'll give me the wheel is clockwise, I flip it. In which direction did I spin? Same, right? Same as the initial one. So let's do anti-clockwise. Let's do to spin it in the anti-clockwise direction. I still have some angular. Right, so now the wheel is spinning anti-clockwise. Yeah. You'll give it to me, still spinning anti-clockwise. I'll rotate it. In which direction did I spin? Clockwise or anti-clockwise? Anti-clockwise, right? Okay, so what's the answer for that conceptual question? Right, so here you were stationary and you flip it, so you're spinning in the opposite direction. You saw that, yeah, that's just a backup video. So the turntable span in the same direction as the wheel before, right? The wheel was spinning clockwise, he handed it to me. when I flipped it over, I spin clockwise, right? So why is that the case, right? So initially, here's the initial condition, right? That's me sitting on the stool. The wheel was rotating in the clockwise direction. Right-hand rule says that the moment of inertia, I'm sorry, the angular velocity is pointing upwards because you curl your fingers in the direction of rotation of the wheel. Your thumb points in the direction of the angular velocity, which is also the direction of the angular momentum. So initially, the angular momentum was upwards from the wheel. Okay? And then, all right, so you have this initial upward angular momentum. When I flip the wheel, so that the wheel is now spinning in the anti-clockwise direction. If you do right-hand rule, your fingers will curl in the anti-clockwise direction. The angular velocity and angular momentum will now be downwards. So this is the angular direction of the angular momentum of the flip wheel, which is now downwards. Conservation of angular momentum says that the turntable should spin in this direction with this much magnitude, with twice the magnitude, in order to conserve the initial angular momentum. Yeah. So if you have, after the flip, after flipping the spinning wheel, I now have the wheel has a negative angular momentum. Okay, to counteract this negative angular momentum and go back to the initial upward angular momentum, the turntable has to spin clockwise so that you have this upwards angular momentum, and the wheel needs to spin twice as fast, right, to have twice as fast angular momentum. So if you add the angular momentum after flipping, that should equal the angular momentum before flipping. Got it? Yeah. And it's the same case if you have the initial anti-clockwise angular velocity. The only thing that will change is that the wheel will have this angular momentum of the wheel will be downwards. My angular momentum is 0. That's the turntable's angular momentum. And then afterwards, when the wheel's rotation was flipped, so this is now the final angular momentum of the wheel, then I should rotate in the anti-clockwise direction turntable in order to conserve the angular momentum.
That would be for the anti-clockwise. I think that would be upward for the anti-clockwise.
Anti-clockwise. Anti-clockwise, yes. Yeah. This is clockwise. Yes, you're right. So I just repeated, yeah, this is clockwise. So actually what is shown here, this is the anti-clockwise case. Yeah. Cool, thanks, Cameron. Any question about this conceptual example here? Was that clear enough? How, yeah. Okay, good. Right, so let's do another demonstration. Any volunteers this time? Someone wants to spin around, and yeah, you can come over. This one is Yeah. Right, so notice how he's spinning, and in one moment he'll stretch out his arms. Right, what can you observe about his angular velocity? And you can draw in your. Can you observe a difference for when he stretches out his arms and when he pulls them in? Are you busy now? Let's stop this. Can you? And he made it to his chair, so I think it's okay. Not so dizzy there. So did you observe any change for when he stretched out his arms and when he tucked them in? What changed? The angular velocity. When was the spinning wheel faster? When he's tucked in, right? So what's going on there? Right? Conservation, it's still conservation of angular momentum. Okay. The angular momentum when his arms are tucked in, it's still moment of inertia times angular velocity. Similarly with the outstretched arms, the angular momentum is still moment of inertia times angular velocity. Right? What change? But conservation of angular momentum says the angular momentum should be the same regardless of whether he tucked in or stretched out his arms. But what changed is the moment of inertia. So moment of inertia is the distribution of mass around some axis, right? So when he stretched out, when he tucked his arms in, okay, then you have a smaller moment of inertia. A smaller moment of inertia will require a larger angular momentum. Larger angular velocity, and therefore he spun faster. Whereas when he stretched out his arms, he is essentially increasing his moment of inertia because the mass is distributed farther away from the rotational axis. So you have a larger moment of inertia in the outstretched arm, and that effectively decreases the angular velocity. Right? So increase the moment of inertia, you should decrease the angular velocity so that the total angular momentum will be equal to the condition before. Okay. Recalling, of course, that moment of inertia resists the change in rotational motion. Right, and there's an interesting video that demonstrates the importance of the concept of conservation of angular momentum. If I can make the sound work, hopefully, or maybe I should use this computer, my projector. Hopefully the sound, yeah.
For decades, the Winter Olympic Games have drawn people from across the world to marvel at breathtaking athletics on the snow and ice.
For decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases.
Ooh,
And this is how skaters...
delay there. Quite cool, isn't it? Right. So yeah, we're back here. Yeah. So conservation of angular momentum, it's just playing with the moment of inertia and its relationship to the angular velocity. Cool. So now let's look at some examples, some numerical examples, and see how we apply conservation of angular momentum and the concept of angular momentum to some worded problems. So here, say you have a disk of mass m and radius r. The disk is rotating around the z-axis. I should show the picture here with some angular velocity omega I. And then there's a second disk. It's not rotating, stationary, and it's dropped on top of the first. So there's some friction between the disks, meaning that the top disk will not slip when it's dropped onto the first disk, and therefore the two disks will rotate together with some angular velocity omega f. We want to derive an expression for the final angular velocity, or how fast do these two disks spin around. So the situation scenario is somewhat similar to this animated figure. So disregard the sizes of the disc. I couldn't find an animated figure with similar discs, but it's sort of like this. So the scenario is sort of like that. So the top disc, stationary, it's dropped onto a rotating disc. Then they rotate together, and we want to find what's their final angular velocity. At what velocity will they rotate together? Right? Okay, so that's the scenario there. So before we have two events. One that's before dropping the top disc, and one after dropping the second disc, and the two discs are rotating together. So in the initial condition, one disc is rotating, so there will be some angular momentum because you have angular velocity in the bottom disc. So therefore, the total angular momentum before dropping will be equal to the moment of inertia of the bottom disc times the angular velocity of the bottom disc. Of course, the angular momentum of the top disc is 0 because it's not rotating. Yeah. After dropping, they now rotate together. So your final angular momentum will consist of the angular momentum of the bottom disc plus the angular momentum of the top disc. Right. So this is the angular momentum of disc 1, the bottom disc, angular momentum of the top disc, disc 2. Okay. So they rotate together because they merge together and they rotate together, and therefore they should have the same final angular velocity. Okay. Just like the collisions that we talked about when we learned about linear momentum, right? When two objects collide and they move together, you can think of them as a single object, and so you add their mass together and they have the same final velocity. So it's a very similar concept here. The two disks are merged together, so you can add up their moments of inertia, so they have this total moment of inertia times the angular velocity, which is the same for the two disks. Right? A conservation of momentum says that the angular momentum before should be equal to the angular momentum after. So then, right, the moment of inertia of the rotating disk times its initial angular velocity should be equal to the total moment of inertia of the two disks times their final angular velocity. So then we have identical disks. For a disk, the moment of inertia is 1/2 mr squared, which you can look up in the tables that I showed in one of the slides in one of the lectures last week, right? So they have the same moment of inertia, 1/2 mr squared. M is their mass and r is their radius. So you can simplify this equation into 1/2 mr squared. Okay. That's the moment of inertia before, of the single disk that's rotating before. But the moment of inertia after will now be mr squared because you have two of these identical disks, right? Okay, then the final angular velocity will be half of the initial angular velocity. Okay, so yeah, the m is mass. Yeah. This one will now be the mass of each disk because yeah, each disk you're adding what you will add will be the moment of inertia, and the moment of inertia of one is 1/2 times the mass. So if you know, this is 1/2 mr squared plus 1/2 mr squared. So this mass is referring to the mass of one disk. So this m is effectively just the mass of one disk because they're identical. What comes into here, if it's just a single disk, like the initial condition, you have half the mass. So if you have two disks, then you have the mass of one. Yeah. All right. How about the type of collision? Is this is this elastic or inelastic collision? They stick together and they move around. Inelastic, what will happen to their kinetic energy? I mean, if it's inelastic, what can we say about the kinetic energy after compared to the kinetic energy before? It should be less, right? Kinetic energy is not conserved during inelastic collision. You can sort of see that from the relationship of the angular velocities, right? The kinetic energy of a rotating object is 1/2 I omega squared. After collision, notice that the angular velocity after collision is half the angular velocity before collision, right? So it will follow that after collision, the kinetic energy will be less, will be 1/4 less compared to before collision. Right? Right. Any question about this example and conservation of angular momentum? Right. No questions? Yeah, maybe you can try this out. I'll give you a few minutes to try this out. The diver comes off a board, initially arms straight up and legs straight down. Her initial moment of inertia is 18 kilograms meter squared. She then tucks into a small ball. Therefore, his moment of inertia is decreased to 3.6 kilogram meter squared. Okay. When the diver is tucked, she makes 2 complete revolutions in 1 second. If she didn't tuck at all, how many revolutions will she make in 1.5 seconds from the board to the water? Okay, the answer is 0.6 revolutions. Yeah, let's see why it's 0.6 revolutions. Okay, so same problem there. Let's write down what's given. Okay, what we know before talking, the moment of inertia, I'll say that as moment of inertia initial is 18 kilograms meter squared. Okay, and then while the diver is tucked, her moment of inertia is decreased because she moved her arms inwards. I'll call that as final moment of inertia. That's 3.6 kilograms meter squared. Okay, what else is given while she's tucked? She makes 2 revolutions in 1 second. That means the angular displacement is 2 revolutions in a time of 1 second. Yeah, 2 revolutions per second. Right, revolutions, this is not an SI unit, so we can convert the angular displacement from revolutions to radians, and we have 2 times 2 pi, because in 1 revolution you have 2 pi radians. So this will be 4 pi radians, which is 12.6 radians for her angular displacement. Therefore, while tucked, she will have an angular velocity. While tucked, her angular velocity, which I say angular final because the condition of being tucked will be the final condition. So her final angular velocity will be angular displacement over time, or 12.6 radians divided by 1 second, because she makes 2 revolutions in 1 second, as given here. So her angular velocity while she's tucked is 12.6 radians per second. This will be the final angular velocity. What we want to find is how many revolutions she'll make if she's not tucked. The condition when she's not tucked, before tucking, we indicate that as the initial conditions. So effectively, first we want to find the diver's initial angular velocity. And once we know the initial angular velocity, we can then use that to determine how many revolutions, meaning what's the angular displacement if she's not tucked. So let's do that. How do we do that? So angular momentum is conserved. Right, so the final angular momentum will be equal to, or I'll just use initial first. Yeah, initial angular momentum is equal to final angular momentum, which means that the initial moment of inertia times the initial angular velocity should be equal to the final moment of inertia times the final angular velocity. Right. Okay, we want to find the initial angular velocity, meaning the angular velocity of the diver if she did not tuck her arms. So that will be just rearranging this equation, or I'll substitute the numbers now. So final angular moment, moment of inertia, final moment of inertia is 3.6 times 12.6 for the final angular velocity divided by 18 for the initial moment of inertia. So the initial angular velocity we can get here will be 2.52 radians per second. Right? So if she did not tuck her arms, she would have this, she would still flip over, right? But her arms are stretched out, or not stretched out like this, but her arms are stretched out like this. She would still flip over, but her she will flip over with this angular velocity 2.52 radians per second. And if she was flipping over with this angular velocity, we will now find her displacement. So with this angular velocity, what will be her angular displacement? So we know the definition of angular velocity is the angular displacement over time. From here, we can then find the angular displacement, angular velocity times time, 2.52 radians per second if she did not tuck her arms. Right. The problem says how many, if she did not tuck her arms and she's going, she's rotating at this angular velocity, 2.52 radians per second, how many revolutions will she make in 1.5 seconds? So the time here will be 1.5 seconds, right? So this will be an angular displacement of 3.78 radians. Okay. Right. The question specifically asks how many revolutions. What you've gotten is angular displacement in radians, so you need to convert radians to revolutions. So convert radians to revolutions. Okay, 1 revolution, of course, is equal to 2 pi radians. So delta theta will be 3.78 divided by 2 pi. Yeah, so then the angular displacement will be 0.6 revolutions. So she won't even make a full turn, okay? Just 0.6 of a turn and she'll already hit the water. All right, any question about the solution to this problem here? What? Cool. Yeah, fine. You're right, yeah. Because you can just keep it, yeah, you can keep it in hertz all throughout, and then you don't have to convert in the end. Because, yeah, as long as you keep it in hertz consistently throughout. All right, no questions. So have a good day, everyone, and I'll see you in tomorrow's lecture.